Mole calculations. Matter in moles, molar mass, molar volume, percent composition, empirical and molecular formulas, then combustion analysis, hydrated crystals, and finally a selection of problems fully solved. Any substance contains Avogadro's number of representative particles, or 6.02 times 10 to the 23rd representative particles. So here's some examples. 1 mole of carbon atoms, 6.02 times 10 to the 23rd atoms of carbon. 1 mole of pickup trucks, 6.02 times 10 to the 23rd pickup trucks. Representative particle refers to the species or types of particles in the substance. For example, atoms, molecules, formula units, or ions. So let's start with a molecule of water, which is 18.0 AMU, and we want to find out how many molecules are in 1 mole of water, where we get up to a laboratory sample size over here. Well, there's 6.02 times 10 to the 23rd molecules of water. Notice again, we'll get to this a little bit later, the relationship between the AMU and the grams. They're the same. So if we have 1 mole of carbon, we have 6.02 times 10 to the 23rd carbon atoms. In 1 mole of water, there are 6.02 times 10 to the 23rd water molecules. And we're going to call that molecules, and that works for any molecular or covalent compound. In 1 mole of salt, sodium chloride, there are 6.02 times 10 to the 23rd formula units. We use that for ionic compounds. Calcium deficiency can cause osteoporosis, weakening of the bones. The minimum amount of calcium in 1 milliliter of blood should be around 1.3 times 10 to the 18th atoms. A patient has her blood tested and the lab finds there are 3 times 10 to the minus 5th moles of calcium in the blood. Is this patient at risk? Well, if you click on this, well, first try and work it yourself, and you can pause this video if you need to. And when you're done, okay, let's just click here. Calcium deficiency can cause osteoporosis, which is a weakening of the bones. The minimum amount of calcium in 1 milliliter of blood should be around 1.3 times 10 to the 18th atoms. A patient has their blood tested, and the lab finds there are 3 times 10 to the minus 5th moles of calcium per 1 milliliter of blood. Is this patient at risk for osteoporosis? Well, here we have Avogadro's number, 6.02 times 10 to the 23rd mole inverse, which means that's particles per mole, times 3 times 10 to the minus 5th moles. All right, that's up there. That's the moles of calcium per 1 milliliter. That tells us that there are 1.8 times 10 to the 19th atoms of calcium, which is greater than the minimum amount required. So, the normal range is exceeded. That's just fine. The patient is okay. In order to do calculations involving ionic and molecular compounds, we're just going to have a quick review here. The total number of atoms or ions in a compound depends on electronegativity and bonding. So here's ionic compounds. Sodium chloride, we have 1 sodium ion, 1 chlorine ion. Potassium chromate, 2 potassium ions, and you see the plus there for the potassium. 1 chromate, CrO4, 2 minus, and then tin hydroxide. And what we have here is 1 tin ion, and we have 2 OH minus ions. Molecular compounds, covalent compounds, water, 2 hydrogen atoms, 1 oxygen atom, C6H6, 6 carbon atoms, 6 hydrogen atoms. So over on the left side, we're talking about ions. The right side, we're talking about atoms. Chemicals are composed of more than 1 molecule or formula unit. And remember, molecule forms molecular compounds or covalent compounds. Formula unit is ionic compounds. To indicate more than 1 molecule or formula unit, add a coefficient in front of the compound. Coefficients are integers, 1, 2, 3, 4, 5, 6, etc. So right here, we have 6 molecules of carbon dioxide. You can count them. How many atoms of carbon and oxygen are in 6 carbon dioxide molecules? Well, you can either count each one or just use this guy. And carbon, you multiply the 6 times 1 carbon, you get 6 carbon atoms. And for oxygen, 6 times 2, because there's 2 atoms in the molecule, 6 times 2 is 12. So let's fill in the blanks here. We'll start with the ionic compounds. And the first one was done for us. And notice they just multiplied the coefficient times however many atoms were there. So here for potassium plus, 2 times 2, 4. And the ion here, the chromate ion, there's only one of them inside the ionic compound, so 2 times that whole configuration there is just 2. Here, 410 hydroxide, well, there's 4, but there's 2 of them in the ionic compound. 4 times 2, 8. Let's go over to water. Hydrogen, 6 times 2, 12. Oxygen, 6 times 1, 6. C6H6, well, there's a 1 in front of it. You're assuming a 1 if there's no other number there. So we have 6 carbon atoms, 6 hydrogen atoms. Now we're going to convert moles to the number of particles we have. So recall, when we had 1 molecule of water, 18 AMU, in 1 mole of water, which is 18 grams, we had 6.02 times 10 to the 23rd water molecules. So in 1 mole of water molecules we have, this number here tells us that we have 2 moles of hydrogen atoms and then 1 mole of oxygen atom. Here, let me kind of rewrote over that. So 2 moles of hydrogen, 1 of oxygen. So to find out how many atoms there are, we multiply that by Avogadro's number. So this tells us how many atoms of hydrogen we have, and this tells us how many atoms of oxygen. Let's take an ionic compound, same drill. If we have 3 moles of sodium chloride, and remember, formula units are what we use for the ionic compounds, there's our 3, that tells us that we have 3 moles of sodium plus ions and 3 moles of chlorine minus ions. Hemoglobin is a protein that carries oxygen around your body. The formula for it is approximately carbon, hydrogen, nitrogen, oxygen, sulfur, and iron, with various numbers. If a patient has 2 times 10 to the 16th atoms of iron, how many moles of hemoglobin would be present? Hemoglobin, which is abbreviated HB, is a protein that carries oxygen around your body. The formula for hemoglobin is approximately this: CHNO, sulfur, iron, and a whole bunch of atoms. So if a patient has 2 times 10 to the 16th atoms of iron, how many moles of hemoglobin would be present? So first let's find how many moles of iron we have. That's going to be N over Na, where Na is Avogadro's number. So here's our 2 times 10 to the 16th atoms, which was a given, divided by Avogadro's number, and we get 3.3 times 10 to the minus 8th moles of iron. Now, there are 4 moles of iron for every 1 mole of hemoglobin. So we have a unit conversion factor here of 1 mole of hemoglobin divided by 4 moles of iron will give you 1. So we're allowed to multiply the moles of iron over here by this unit conversion factor. So we have 3.3 times 10 to the minus 8th moles of iron times 1 mole of hemoglobin divided by 4 moles of iron. This cancels out, and we're left with 8.2 times 10 to the minus 9th moles of hemoglobin.